So yeah, so it's a pleasure to have Brian Swingle today. So Brian has a very successful, PhD and postdoc history. He did kind of very interesting work on, pioneering work on the connection between, theories of space-time and gravitational theories and quantum information, many body quantum physics. And I learned that today I learned that he just moved to Brandeis, Maryland. So it's good news. And today he's going to tell us about information scrambling in complex quantum systems. So Brian, thanks, and the stage is yours.
Great, thank you for the invitation. Nice to see you all. And yeah, this talk is really going to be about scrambling and chaos, quantum chaos in complex, which for me means sort of strongly interacting in many body systems. And yeah, I'm happy to defer to your local custom, but I welcome questions at any point.
Yeah, we will interrupt.
All right. And yeah, let's get started. So the broad context here is what's sometimes called the quantum frontier. So we all know that quantum theory is incredibly successful theory. It's an old theory. It has deep roots. But especially in a high complexity regime, there are sort of qualitatively new things to understand and discover. New kinds of phenomena, new phases of matter, new models of computation, new insights for black holes, as we were discussing before the talk, both in theory and experiment, and then new capabilities as well. So new kinds of experiments that are now possible that really could only have been dreamed of in previous decades. And this is really, I think, a very exciting time. My particular background is strongly interacting electron physics. That's where I started my studies. And in that context, there are many famous, interesting phases of matter. For example, on the left, I'm showing you the fractional quantum Hall effect, which is a situation where you have electrons confined to a two-dimensional layer in a strong magnetic field. And you observe this very exotic, what we now think of as topological, highly entangled states of matter. On the right, you have high temperature superconductivity, the famous phase diagram of the cuprates. You have the superconductivity down here at low temperature, but all these other exotic regions, strange metals, pseudo gap, etc., where again, we don't know exactly what's going on, but many of the leading theories of this involve some degree of high quantum mechanical entanglements between the constituent degrees of freedom. These are situations where you have some microscopic degrees of freedom like electrons, but really there's some emergent collective degrees of freedom, which are often highly entangled or arising from this highly entangled electronic state, that are the right way to think about the physics. So these phenomena are old, but entanglement and quantum information are giving us new ways of thinking about them. Of course, there's also the more direct connections, including to simulation and to computation. So on the left, I'm showing you this famous experiment with the Rydberg atoms in the group of Lukin and Vuletic at MIT Harvard. I won't go into the details of this, but just to say, like, as soon as you were able to study, say, 50 atoms in a controlled quantum simulator in this one-dimensional array in a programmable fashion, you kind of immediately found new physics. You found these so-called quantum scars, long-lived excitations in an otherwise thermalizing quantum state. And, we really think that's just the beginning. If you really can build even more powerful simulators that are more coherent, or all the way to quantum computers, which of course is something that many people are thinking about right now, there's kind of this cloud of possibilities. So on the right here is actually a artistic vision taken from an article that was very critical of quantum computing, but I actually think it's a very hopeful picture. It's sort of like this cloud of possibilities, and there's planets. Maybe we're going to understand something about space-time from quantum information. So that's all very great. And in fact, even gravity has benefited substantially, at least in theory land, from quantum information ideas. We know since some time ago that black holes should have an entropy, according to semi-classical Einstein gravity. In fact, if you count the stuff in the universe by entropy, then black holes are by far the most entropic object. So if you're accounting by entropy, then we should all be studying black holes as the most important thing, because almost all the entropy in the universe is probably in black holes. But you see this H bar here, the entropy somehow depends on quantum effects. And as we were discussing at the beginning of the talk, just prior to the talk, there's been a lot of development and understanding of the way that quantum information interacts with black hole dynamics, at least in toy models of quantum gravity. So there's really been a lot of development on a lot of different fronts, and it's, I think, a very exciting time. Today, I want to talk to you about scrambling dynamics of chaotic Hamiltonians. And that has something to do with all of the three different areas I showed you. I'll only touch on some of them, but you'll see as we go along. The basic setting is I want to think about, I have a many-body quantum system. I'm just going to usually think about qubits or some spins. I won't be too specific, except towards the end where I'll talk about experiments with nuclear spins. But the idea is you have some many-body system. Here are these black dots. Time runs up, and they're going to evolve according to some isolated system dynamics, just according to some Hamiltonian H. And this Hamiltonian H is going to have the property, the intuitive property at least, that it's chaotic, that it is in some sense, it'll, maybe have some interactions, and, there's no free particle description here. Somehow this is a really, truly complex Hamiltonian that can generate entanglement, etc. I'll be more precise about what I mean by chaos in a second. That's itself a complicated and interesting subject. But the basic question of scrambling is the following. If I put in some simple information, so suppose I put in at the bottom a simple state where I encode information in the state of the first qubit, the first spin here. Then I evolve the system for a long time. The information gets scrambled up, as we say. And because of unitarity, the information must come out at the end in some form. But what scrambling means is that the information is not available from any simple probe. So if you have access to any small collection of qubits in the final state, you essentially can't learn what the information was. Even if you take measurements of different small sets of qubits and superpose them in some way, you still can't learn. You really need to have coherent access to a large fraction, more than half of the degrees of freedom, to learn something substantial about this information. So that's kind of the essence of scrambling. It's taking some simple local information, scrambling it up into a complex form that's no longer observable to simple probes. Okay. So let me give you just something to hold on to, something very concrete. Here's one of our favorite examples of a chaotic quantum many-body system. This is just spin half chain. We have some ZZ interactions here. We have a magnetic field in the X and Z directions. So this term favors the spins to align, and this terms here favor the spins to point in a certain direction. But I'm not interested in the ground state of this Hamiltonian. That's not what I'm thinking about. I'm interested in the highly excited dynamics near the center of the spectrum. And if you plot the energy spectrum of this Hamiltonian, it has extreme values at some plus and minus values, and then near zero energy is the center of the spectrum, which corresponds roughly to infinite temperature. Here are two such states. One of them is the initial state psi1, it's all plus in the y direction. The other is the initial state psi2, which is all plus except for the first spin, which is now minus. So these two states, they're perfectly distinguishable. They're orthogonal states. They have exactly the same average energy right in the middle of the spectrum. And they just differ by the value of this first qubit. Okay. And now here is the time evolution of that system. This is just the exact, I put it in the computer with 14 spins and compute. And I plot on the y-axis the expectation value of the first spin, the y component, right? And the x-axis is time and units of the nearest neighbor coupling. And you'll see at early time, these two are perfectly distinguishable from this measurement of the first spin. The psi1 state has sigma y as +1, and the psi2 state has sigma y as -1. But as time goes on, there's some finite time physics here. But then after a relatively short time, these two curves look essentially the same. So much so that if I covered up the early part of the diagram, you probably wouldn't be able to tell me which curve came from one and which curve came from two. So this is just one observable, one example where these two states at late time look the same. But if you can go in the computer and you can compute any other simple observable, you know, sigma on any other spin or pairs of sigmas, etc., and it will look qualitatively similar to this, right? This is a finite size system, so there are some fluctuations. That's what this wiggles at late time are. But basically, you're seeing thermalization. These two states have the same energy. They're thermalizing to look locally like a maximally mixed state. That would be the equilibrium state at infinite temperature. But nevertheless, they're still perfectly orthogonal. So there is some very complex measurement you can make that will distinguish them, but nothing simple, nothing local.
There will be a resurgent if I wait long enough.
That's right. Yeah. Yeah. You can actually like go as long as you want, and you'll see that this line is like flat up to exponential time, and then after that, it can start doing something interesting. But you don't typically get resurgences until doubly exponential time. So it's really a quite, it does not matter for any practical purpose in a system of more than, say, 30 spins. Okay, so that's the phenomenon, roughly speaking, at a very high level, which I want to talk about today. And before I go on, I want to just tell you why I think it's interesting to think about this phenomenon at this time. The first, as I already alluded to, is that there are many new experiments that can now probe relatively long-time dynamics of isolated many-body systems. Of course, in any experiment, you're not perfectly isolated. Eventually, the environment will have a substantial influence. But we're getting better and better at isolating for time scales long compared to the microscopic scales in the Hamiltonian. So you can evolve for many inverse J before you are losing coherence or you know, some noise or other sources contaminating your physics. And in this context, these far from equilibrium experiments are particularly natural, and they often relate very directly to scrambling and chaos. They're probing thermalization or the lack thereof and related questions, and these have intimately to do with scrambling and chaos. The second reason is sort of from a theory point of view that quantum information has given us a lot of new insights and tools for thinking about scrambling. In fact, you know, the idea of scrambling was something that the word scrambling appeared in the black hole literature some years ago, the work of Sekino and Susskind. But, you know, it wasn't really information focused at that time. It was really just talking about thermalization. But now we understand that it really has information is kind of the right way to think about it. And it's also, as I'll show you later, given us some tools to compute, which we didn't have before. And now again, in the context of quantum gravity, scrambling is also very important. Because it turns out black holes are in some sense the fastest scramblers in nature. That's an interesting story, which I won't tell you today, but it's a nice story. And scrambling is very important for the way that quantum information is processed by black holes. And it helps us understand how to at least relieve the tension of the information problem, as we were discussing before the talk. And then finally, coming back to one of my early motivations, you know, I'm still very interested in dynamics of these many-body systems. In particular, you know, the classic hard observable is transport observables, so electrical thermal conductivity, etc. When you don't have quasi-particles, when you have strong interactions and disorder, you know, this is an extremely difficult problem. There's no, you know, framework or formalism for tackling this in general. Now, there won't be, but on the other hand, it seems like there should be more we can say. You can always go do the experiment or run your quantum simulator, but many of us think that there should be much more we can say from a sort of classical simulation point of view by properly understanding the way that information is scrambled up and that quantum systems evolve in a coarse-grained sense. So that's also something that we can hope to gain insight into by thinking and understanding quantum chaos and scrambling. So let me pause here and ask if there's any questions about the setup or the motivations. Okay. So then what I want to tell you about for the bulk of the talk is this idea of the quantum butterfly effect, what it is physically, a picture for it, how we compute, and what we think the universal behaviors are. And then in the final part of the talk, I'll tell you about attempts to measure this in experiment. In particular, I'll focus on experiments in the context of nuclear spins, nuclear magnetic resonance experiments, where they actually can measure this in some form. And it seems like there's something to understand there and something interesting. Okay, so let me get started. So let's go back to our two states, psi1 and psi2. And let's ask, what is this operator or measurement that distinguishes these two states? I said there was some complicated thing you could do to tell them apart. And formally, it's easy to write down what it is. It's just the Heisenberg operator version of that initial perturbation, the sigma 1z, which flipped the spin from plus y to minus y. And you can think of this as sort of like a version of the butterfly effect, because if you did not have the perturbation, then going forward and then going backward does nothing. You just fast forward the tape, then rewind the tape, you end up at the same place. But if you place this perturbation in the middle, then even if the perturbation is small, because the dynamics is chaotic, what will happen is that the forward and backward evolutions will more and more fail to cancel. And you'll end up, if you go forward for a while and then backwards, you'll end up at a very different place after a while. And this is what I'm going to call the quantum butterfly effect. I'll give you a kind of a fun analogy that I like. So I hope you've all had the pleasure of trying to assemble these wordless IKEA furnitures at some point in your life. It's a bit like you're assembling this nice cabinet here. You've gotten to the 34th and final step, and you realize there's a screw missing. Okay, so you try to figure out, what is this screw, right? You go back, you look through the book, and you see, okay, on step 2, I missed a screw. Now, pretty much the only way that you can get the screw back in is by undoing all the steps back to step 2, putting the screw in, and then redoing the steps. Right? So microscopically, this cabinet is very different from the way it was without the screw. But macroscopically, it still looks like a cabinet, it still holds books, as long as this wasn't a load-bearing screw. And that's kind of a picture of thermalization. So these two cabinets look the same globally in some sense. They can both carry books, but they differ macroscopically in a way that's hard to address with a simple procedure in the final state. Okay, so here's a more quantitative, or a sort of a more qualitative picture for qubits. So let's again think about our array of qubits in space and in time. And I'll write the forward interaction as these orange blobs. So you can think of this as just nearest neighbor couplings between different of these spins, or as the trotterization of your favorite quantum spin chain Hamiltonian, however you like. And there's also the backward evolution. And if I don't put any perturbation in between, then because these evolutions are unitary, they simply cancel out to give me nothing at the end of the day. So going forward and going backwards is the same as doing nothing. Okay, but now let's suppose I put the butterfly in there and I try to do the same procedure. Well, at first, if this butterfly effect, this single spin flip, is localized, then most of the gates will still cancel. But you can see at the center, this particular pair of interactions doesn't quite cancel because this butterfly wing flap here inhibits the cancellation. And now you're generically going to have some kind of expanded perturbation or blockage, which has gone from being on one site to now being on two sites. So this will just generically be some non-identity operator supported on these two sites. And now you can keep trying to cancel more. And still you can cancel most of the evolution because of locality. But now this expanded blockage on two sites is going to inhibit the cancellation of now two gates on the top and the bottom. And so again, the blockage grows, the perturbation grows. And you can sort of see that this is going to keep going. If I keep trying to cancel more and more, the blockage keeps growing and growing and growing. And as this picture suggests, that your baseline intuition should be that the growth of the perturbation is going to be ballistic with time. That's essentially the maximum that it can be. If you're familiar with a Lieb-Robinson bound, this is can be viewed as a version of that. But the speed that we're going to get out at the end of the day is not the same as the Lieb-Robinson speed. Okay. So we have this expanding structure of this perturbation. And we want to sense or measure somehow how large the perturbation has grown. That's the goal here. And the way we can do this is by trying to sort of probe this growing operator using some kind of simple probe operator. And the simplest way to do this proceeds by thinking about commutators. So on the top, I have this big blue structure I just showed you how to think about in terms of partial cancellation of forward and backward evolution, starting from a small perturbation. And then I put a little probe here, V. And the idea is if the probe operator is living on some qubits, some sites that are far away from this perturbation, then it just commutes. I can act with it after the perturbation or before the perturbation, and it doesn't matter. These two are the same, and so they commute. On the other hand, if the operator has some overlap with this blue structure, then it doesn't perfectly commute. And you can imagine that the deeper you get towards the center of the perturbation, the more these things fail to commute. Okay, so I should be able to measure the spreading, the size of this cone and the strength of the perturbation by looking at commutators. So there's a commutator. The simplest thing you could think of would be to look at the expected value of the commutator. And that is a nice physical object. It's the linear response, so something we're familiar with. However, it turns out not to be a really good diagnostic for our purpose because this expected value is typically 0. You have a system which is chaotic, which is thermalizing, which means it's losing memory of its initial condition. It's forgetting where it came from effectively. We already saw that in our little simple spin chain example. And so what you find typically is these commutators will just vanish at late time. So maybe they're sensitive at early time, but if you really want to probe the asymptotic time dynamics, then this can't do it for you. And the next simplest thing that you can look at then is not the expected value, but the variance of the commutator. So the commutator is not 0 as an operator, but its expected value is. And so it's natural just to look at the variance. And that's what this quantity capital C is. It's the expected value of the commutator dagger with itself. If you've followed the recent quantum chaos literature, you may have heard about out-of-time order correlators, OTOCs. When you expand this commutator out, some of the terms there are OTOC terms, and some of them are more conventional time-ordered correlators. But I think it's physically nicer to think in terms of this commutator directly, so that's how I'll present this story. Okay, so what does this thing look like?
So you're going to study just the square commutator?
That's right.
The expectation value of the commutator itself.
That's right. So what I'm saying is the previous picture I gave you in terms of spreading, etc. I'm going to formalize that by studying this object, and this object will be how I characterize all of that physics.
And the square, taking the square just to get a positive.
Yeah, just because the first moment vanishes, so I'm looking for the simplest thing which doesn't vanish and probes the physics I care about. Okay. I mean, there are a lot of other reasons why this is a nice thing to consider, but
you claim that this is basically equivalent and has the same physical context as the OTOC, or?
Yeah, that's right. If you expand this pair of commutators out, there's just 4 terms.
Yeah.
2 of them are time ordered, 2 of them are out of time order.
Yeah.
And in particular, if W and V are unitary, then actually the only terms that are non-zero, that are not just identity, are the out of time order ones.
I see.
So it really contains the same information in a very precise sense as the OTOC.
Okay. Mm-hmm.
Yeah. All right.
Mm-hmm.
So here's how you should think about this. There's the baseline picture you should have in your mind. I think W is the wing flap, V is the probe again. The distance between them is R. So I'm plotting R and at some fixed time, the commutator. And so you see when the distance between the perturbation and the butterfly is small, then you have some kind of strong level of non-commutativity. We're reflected by this plateau region. When R is much greater than some value, the non-commutativity is small. And there's a crossover region where you go from being non-commuting here to commuting at large separation. Okay. Now, what sets the scale of the region here? As I alluded to, it's essentially ballistic. So now if you plot contours of constant commutator in space and time here, what you'll find is that at large space and time, they look roughly like straight lines. And the slope defines a speed, which we call the butterfly speed. So it's like the effective speed at which this spreading operator is growing as you evolve the system in time.
So that's your definition for the butterfly velocity.
That's the definition of the butterfly velocity, yeah.
That's the Lieb-Robinson velocity, right?
Right, no, sorry, yeah.
It turns out, so it's certainly bounded by Lieb-Robinson velocity, upper bounded, but in practice, it is less than that. I mean, the Lieb-Robinson velocity is already, depends on exactly how you bound the terms, etc. But this is really, the way we think about this is a state-dependent velocity that really is related to how this commutator is behaving. So you'll get a definite answer for infinite temperature. You can get a different answer for finite temperature. For non-infinite temperature, it can be less. At low temperature, for example, in a dilute gas, this is like the speed of sound or close to it. So we know a lot about this thing, and it is upper bounded by Lieb-Robinson, but it's not the same.
So the main difference is that Lieb-Robinson is independent of the state. It's like,
that's right. Lieb-Robinson is a state independent bound, and this is really a state dependent, feature that's observable.
okay.
Also, I'll just mention a technical thing. Lieb-Robinson bounds the operator norm of the commutator, which can be different than this like Frobenius norm. So that's a technical point which is important in some contexts.
Right. Yeah.
Okay. So I've introduced the kind of key theory quantity and given you a sketch of its behavior. I'm just going to quickly flash some slides. There's too much information here to absorb in detail, but I just want to give you a flavor of what the community has come to in terms of understanding the physics of this thing in various kinds of many-body systems. There's at least two classes. I mean, here I'm talking about chaotic systems. If you include free particles or like the Heisenberg chain in 1D, you get even more sets of possible behaviors, and we don't understand. Well, Heisenberg we don't understand. Free particles we do. This picture here won't be true anymore. Like for free particles, you'll still have growth, but then the commutator drops again at late time. So this is really something specific to chaotic systems. But there's sort of two classes of models here. One are what I call large N models. So ADS CFT is in this class. The ON vector model at large N. Various kinds of mean field models have this flavor. Models where there is like a long length scale. So like weak coupling, where you have a big separation in scale between like the thermal length and the inelastic mean free path, can also be thought of as in this class. And in that class, what you find is that if you look at the commutator as a function of space-time, again, this is in the region where the commutator is small, so I'm just focusing on the early growth. You'll find that there is this light cone, a light, I mean, it's not really the speed of light, but some effective light cone. And if I look at fixed time, there's a sharp crossover from the region where the commutator is small to the region where it's large. Okay. So the width of the front, the width of the crossover is constant in time. Then there are also these random unitary circuit models where you still have a light cone shown here, but as the picture suggests, the width is getting broader as you go. And in fact, for these models, as shown by the authors here in some pioneering studies, the width of the crossover in 1D grows diffusively. So the operator is expanding ballistically, but it's also getting fuzzier at its edges, and the fuzziness is growing like the square root of time. So the field was, these are two classes of systems. One question you can already ask is one of these generic? Are there two universality classes or more universality classes? Or is everything, in certain limit, the same as type 2? The conjecture is that this random unitary kind of physics or result is the generic one, and I'll show you why we think that in a second. But there are these two classes. Just Flash, we can do a lot of calculations in various kinds of field theories in the ON model, in the disordered metal in 3D and perturbation theory. So this is, of course, a well-studied problem in other contexts. We can do calculations in ADS-CFT, and you can get various results. So for the ON model, it's a conformal field theory. The butterfly speed is essentially the speed of light. In the metal, you have some interesting temperature dependence. And you get various results. Again, just give you a flavor, how do you actually compute this? Well, for the ON model, for example, you need to sum diagrams. So it's a real-time calculation at finite temperature. It's an interesting and non-trivial calculation. You're relying on large N to give you some controlled set of diagrams you resum. And you end up resumming some sort of ladder diagrams as indicated here. And you look for poles in this beta salpeter equation, which indicates some growing mode. And you try to find the fastest growing mode, and that's what controls this, this exponential growth that I showed here. That growth is sometimes related to a Lyapunov exponent, some kind of quantum Lyapunov exponent. But as you can see in type 2, it's not a universal feature. So you don't always have this exponent. And so I'm not going to talk in more detail about it.
So Brian, in this class too, do you have like also Hamiltonian-based models, or is it really restricted to kind of unitary? This circuit models.
Yeah, it's a great question. I'm actually coming to that right now. So we do have Hamiltonian models. This is a kind of mixed model. So this is a Hamiltonian model that we wrote down a couple of years ago, where you have Hamiltonian, but the Hamiltonian couplings are Brownian motion, right? So they're white noise couplings, right?
So they have some stochastic noise?
Yeah, it's stochastic noise, right? So a given realization of this thing is like some Hamiltonian with some time-dependent couplings, but it's a unitary evolution. And then you can average over the time dependence of the couplings to give you some theoretical control. And there's a microscopic picture in terms of you can expand this operator in terms of strings of polys. There's like a complete basis for all operators, and formulate the physics in terms of the dynamics of these poly strings. And again, this is just to give you a flavor. I'm happy to answer more questions about this now or afterwards if you have them, but just to give you a flavor, you can relate the physics of this commutator to the average weight dynamics of the poly. So the weight means how many non-identity polys are on a given site. And basically this grows with time in some way, and you can formulate a closed differential equation for that weight by looking at some master equations, etc. And what you find at infinite n is that you get some very nice equation called something similar to an equation called the
Fisher. And here is the number of spins, and you have some clusters, and
n is the number of spins in each cluster, right? So it's a kind of large n limit.
Mm-hmm.
And so,
can you explain again what you mean by Brownian coupling?
Sorry?
What did you mean by Brownian coupling?
Oh, I just meant the couplings between the spins. Think about it, you have every possible like SI, SJ coupling between different spins. And
so is it random or it's time dependent? For me, Brownian
the exchange, yeah, it's time dependent and random for every pair of sites in a cluster and between neighboring clusters. Does that make sense?
But I don't know. So who is doing a Brownian motion here?
The coupling is
the couplings are white noise. So if I integrate them, they're doing a Brownian motion.
Good. Okay, that was clear. Coupling white noise, I understand.
Yeah,
okay.
Yeah.
Thank you.
Okay. So at large n, at infinite n, you get this nice equation, the Fisher-Kolmogorov-Petrovsky-Piskunov equation, which comes up in many contexts, ranging from forest fires to invasive species dynamics. It was first talked about in this context, the context of quantum chaos, by Farrow, Yaffe, and Aligner. Here we derive it again for this model. And what this equation predicts is that you have sharp front. Okay, so this model recovers the large N physics that you had in these type 1 things, which was not something you could get with the random circuit models. But moreover, we can also go to finite but large N and study how corrections arise. And it turns out what you do is you take this equation and supplement it with a noise term. And this noise term is not the noise of the couplings, it's really quantum fluctuations. We can make that quite precise. So it's really saying that here it's like the operator is growing in a deterministic way because it's a large N model. And here at finite N, there's some quantum fluctuations in how the operator grows. And thanks to a nice analysis by these authors some years ago, you're able to show that this equation has at long time solutions where the front is broadened diffusively. The basic physics is relatively straightforward. The front is moving ballistically, but it's also executing a random walk. And so once you do that random walk at large time, you get this diffusive scaling. It's very non-trivial to figure out what the diffusion constant is. It turns out to have this very interesting 1/log n cubed behavior, which I won't have time to explain here. But anyways, it does give you diffusive scaling. Okay. So this
noise, you're saying this noise again, white noise, or is
it is white noise, but it's not additive noise. It depends on C. So it's some kind of multiplicative noise. It preserves the light cone, but it has this non-trivial effect of giving you the diffusive broadening.
Brian?
Yes.
Is it obvious that there is a single butterfly velocity? For example, if you mix like 2 different types of degrees of freedom, electrons and phonons, for example?
Yeah, good question. It's not completely obvious. Essentially, what the intuition for why there is just one velocity is, or why you should expect just one velocity, is that if there's any coupling between these two, then they kind of will equilibrate amongst themselves at sufficiently long time, so that if you started with an operator in the electron sector and it grows, it can turn into a phonon operator. Like that's part of its expansion. And then so whatever you get has to be consistent with the fact that electrons can turn into phonon operators and vice versa. And so for this reason, we sort of expect that any generic operator will ultimately grow the same way, no matter what its microscopic character, up to things like symmetries and, constraints that you have from the Hamiltonian itself. And that's something we can check in some contexts, but it's not something, there are subtleties. Like if you couple a very slow mode to a very fast mode, we don't know what the butterfly velocity will be quantitatively. We sort of think there will be just one of them, but we don't know how to necessarily compute that. So it's a subtle question that I would not say we fully understand at this point.
Thanks.
Where is the 2 coming from in this equation? What's special about 2? 2 minus
Oh, that's
3.
just how we normalize the commutator.
I see. Okay.
Yeah, it has no special meaning. Okay, so the takeaway from this study that we did was that this type 1 behavior is unstable, and if you have any kind of quantum fluctuations, you expect to have type 2. So that seems like the generic thing. Let me skip this. There's just a way. There's a way to put all these different forms in one framework with a parameter p, an exponent. So the large N behaviors and the random circuit behaviors can all be put in this framework. And even non-interacting particles can go in this framework. So it's a nice framework. And so what we wanted to do was just to actually look at our favorite spin chain again, some more or less generic quantum spin system in 1D. We'd love to do 2D as well, but that's of course harder computationally. And just compute at large size and see, like, is it ballistic with a sharp front? Is it ballistic with a diffusive front? Is it something else? And I'll be very schematic here, but the way we compute this is using a tensor network technique. So again, a kind of quantum information inspired technology coming in here, theory technology. the idea is to approximate this growing Heisenberg operator as a matrix product operator. And here I'm applying the entanglement of that matrix product operator as a function of space and time. The butterfly starts here at site 50. And the blue region is low entanglement. The yellow region is high entanglement. And the reason why this works essentially is because in the yellow region, you're making a bad error when you truncate this MPO to a constant bond dimension. In the blue region, it's fine, but you're making a bad error in the yellow region. However, because of this light cone physics, that error turns out not to propagate too strongly outside the light cone. And so we expected and numerically found that you can get good convergence of this operator sort of ahead of and up to the light cone with a modest bond dimension. Okay. And so in particular, all this physics here, this early growth physics where we were comparing different forms, that's accessible.
So what is exactly this graph? What is the quantity you're plotting?
This is the entanglement. So I take this operator and I cut it along some place. Now it's an operator, not a state, but I can just think of it as an operator on a two copies. I mean, a state on two copies, and then I can compute its entanglement. And that's what's shown here. So this is high entanglement.
So it's not the CR previous.
Yeah, it's not the C, it's just the entanglement.
Mhm.
And so the point is, in this, if you wanted to like truncate in this blue region, that's fine. In the yellow region, it's not fine. But the mistakes you're making by truncating anyways there don't actually propagate fast enough to damage the calculation in this region.
Well, what we're plotting is the bipartite entanglement for a cut which is located at X, or
That's right, yeah. This dashed line here.
So is entanglement growing indefinitely?
No, it saturates. There's a maximum amount that it can be, which, because it's an operator instead of a state, would be 4 times the number of sites in a region in bits, or sorry, 2 times the number of sites in a region in bits, because the operator space is 4-dimensional instead of 2-dimensional. But yeah, so it has a maximum value per unit length.
Okay. So the picture would look different if I look larger times.
Yeah, I mean, here, this is actually the actual entanglement in the matrix product operator. So that's why it's limiting, because you have a finite bond dimension, so you can't have more than a certain amount of entanglement for any size region. But yes, the physical system, if I was doing that at large size, it would look different. It would keep growing in this region up to some point.
how do you know that how do you define this local convergence of the MPO, where you're saying that it converges on some region but doesn't converge in another region? How do you check that?
It's a good question. The best we can do, or what we did, was you can take this operator and compute from it the C quantity, the commutator. Mm-hmm. It's actually very simple, because the commutator is just like this times V minus V times this. So you can actually keep the same MPO, but just change one tensor where you insert the V. Mm-hmm. And then it's also nice because when you do it in this way, the squared commutator is the sum of the singular values squared. So there's a very nice way of taking the canonical form of this MPO and turning it into that commutator. So what we check is that commutator is converged in certain regions of space-time. That's the precise statement.
Converge as a function of one dimension.
As a function of bond dimension, yeah.
Okay. Mm-hmm.
Okay, so this is just a sample of the data. Here I'm showing bond dimension 4, which is, definitely not big enough, but actually surprisingly decent already in this very early region, and then bond dimension 32. So in this early growth region, their 4 is already the same as 32. In this sort of larger region, as you go to longer and longer time, these are different separations between the operators, these different curves. So as you go to longer time and larger separation, you start to see a difference between 4 and 32. But then if you go up to using a couple of other tricks, and at 200 sites, we can converge essentially to where the commutator is order 1, say about a half or something. It looks quite reasonable. Yeah, and then this is actually showing a data collapse where I collapse some of the formula I showed you before for the early growth form, so you can extract an exponent from this. But an even better way to do it is to look at the contours. So here's 2 contours of a commutator where it's e to the minus 20 and e to the minus 45. And according to this formula that I flashed, these commutators should have these contours should have a definite time dependence. They should have a ballistic piece and then a sub-ballistic power law piece that depends on the exponent p. So if you take the difference of trajectories of these commutators, of these contours, you're going to get just this p-dependent thing. So then we plot that separation versus time. And on the inset here is log plot. And at very, very long time, or sufficiently long time, you converge onto the line y equals a half x, which predicts that p over 1 plus p is a half, or p is 1. And that's exactly, I don't expect you to follow the details, but that's exactly the value you would have for this diffusive broadening. So the conclusion was we have this controlled calculation, seemingly controlled calculation with tensor network for this ordinary energy conserving spin chain with 1 spin per site. And at the largest sizes and times, but still in a converged region, we get a ballistic front that's broadening diffusively, just as we expected from these random circuit models and from our coupled cluster model.
Okay.
So the conclusion, the current conjecture in the field, the current status is that we have and others have conjectured that this diffusively broadened front is the generic behavior in 1D. We've accumulated a fair bit of evidence for this numerical evidence, various kinds of model calculations. And that's the situation right now. So the conjecture is that there is a universal structure for operator growth in 1D. I mean, there's analogous conjectures for higher dimensions, but let me just focus on 1D for simplicity. Such that any quantum chaotic system, which is generic, meaning not infinite n, etc., will have this ballistic growth plus diffusive broadening. Okay.
In this system, you see a difference between the Robinson velocity and the butterfly velocity, or?
Yeah, I mean this butterfly velocity is a definite number that we just extract, and the Lieb-Robinson velocity depends on how you choose to bound your commutators, but it's higher. It's not the same as this.
Also, for which initial state do you?
This is all done in the infinite temperature state, but you can at finite size study at smaller size using ED study other kinds of states, and it looks similar.
So you think there's no?
You have an expectation that it doesn't depend on the state too much.
You think also in a ground state, close to the ground state, would behave the same, or?
Well, yeah. So if you change the energy density, then that will change the story. So I didn't show this here, but my student Shubayan and I did another study where we extended this to finite temperature. So we studied the same model, but now at non-infinite temperature. So you put some thermal density matrices into those formulas. And then there's an interesting story about how it depends on how you distribute the thermal factors. So if you put them.
But you do numerics at finite temperature, or?
Yeah, you do numerics. If you put them all here, then you get some kind of temperature independent velocity. If you distribute them in between in some way, which is called a thermally regulated commutator, then you get a temperature dependent velocity, which we can also do field theory calculation, etc. So we see this broadening persist at finite temperature. So we think that if you have any finite energy density above the ground state, that this is still generic. of course, the ground state itself, or if you have sort of order 1 energy, not an extensive amount of energy, then that's a different story.
Mhm.
But we think this is the generic behavior for finite energy density. You know, just mention you can also study localization. Like we looked at the Aubrey-Andre-Harper model with a quasi-periodic potential. We also looked at disordered models. You can see these velocities slowing down and collapsing to 0 as you approach localization. So there's a whole lot of beautiful physics that you can see in a new light from this point of view. And precisely because we have this numerical machinery that lets us go to large systems in long times in some regions of space-time, we can actually provide some new information that was not accessible from previous methods. Okay, so let me just flash one more thing really quick, which is how this relates to information spreading again. So I started talking about information at the start. One way you can make this precise is to consider a thought experiment where you entangle, say, 1 qubit, that's your perturbation if you like, with a reference. The reference you then put aside, you don't do anything to that reference. And you let the system evolve in time. And you ask, how big of a region do I need to have access to recover that information, to recover that entanglement? For similar reasons, you can expect that region will grow ballistically with time. And what we were able to argue with, again, some numerical calculations, some calculations in ADS-CFT, and also a precise quantum information argument using something called the Hayden-Preskill protocol, was that the butterfly speed, in the simplest case, determined this information speed.
How do you define it? I mean, you want to find a circuit that basically reconstruct the qubit.
That's
qubit
right. You ask, what's the minimum region I need access to here, so that if I can run an arbitrary complicated quantum computation or circuit, I can distill that Bell pair of entanglement.
Mm-hmm.
And if the region is too small, you can't do that. If it's sufficiently big, you can. And so here we're asking, what's the borderline case? How big does the region need to be so that I can just recover it, with high probability? And that region again is expected to grow ballistically with time, and that's what we find. And we find that the speed of that growth is just the butterfly speed. So this operator growth is really quantifying very precisely just how information or entanglement is spreading in your system. Okay.
But you think again this is generic?
Yeah, this is generic. So we check this formula for spin chains. Now at smaller size now because we need to compute the entanglement as well. That's harder to do. That's not something you can do reliably at very large size with tensor network. So we use a Krylov technique with, I forget, maybe 20-ish sites. Don't quote me on that number, but some reasonable number, the biggest we could do. We find this formula is valid. We can compute all the quantities of interest in ADS-CFT. We find this formula is valid. We can also give a precise quantum information argument using what's called Hayden-Preskill protocol, which is a protocol that you can use to recover the quantum information, which also predicts VI equals VB. So all these different arguments point to the same conclusion that's discussed in this paper here. And there's a generalization of this where you depend on energy density and also entanglement density, how much entanglement you have in the initial state.
But I'm a little confused. Entanglement is not a local quantity. So what does it mean for the entanglement to have speed?
Well, so the precise meaning is, that's why I really call this information speed. So it's like, if you put some information locally, how big a region do you need to have access to recover it? And one way to track that, to tag that information, is to think of it as entanglement with a reference and ask how big a region I need access to such that this region is maximally entangled with the reference. That's the sense in which I'm tracking the speed of entanglement. But I agree with you, it's not a local thing. And it's not that entanglement itself has a speed, it's that the size of the region that is entangled with the reference grows in some characteristic ballistic fashion.
So that's how you practically compute this quantity.
What goes into this claim on the following slide is we compute this mutual information on its own, and we compute the butterfly speed separately, and we just, with no parameters, match them. So they just agree.
But the mutual information is saying you actually have an extra subsystem.
That's right. Yeah. You know, in the code, you have, you know, whatever, 19 sites plus one reference, you entangle them, and you just literally evolve it unitarily, compute the subsystem state, and compute the mutual information between the reference and the subsystem state.
I see.
And we define this VI as asking the mutual information to be equal to 1. Its maximum value is 2. That indicates maximal entanglement. So 1 is like just where it becomes sort of, just where it crosses over into definitely being entangled. If mutual information is bigger than 1, you know there's entanglement. And we checked that it did not depend too much on that precise value. But so we just literally track the contours of mutual information equals 1.
That's the mutual information between this reference and the
reference in the purple region.
That was really helpful. Thank you.
My pleasure. All right, so I'm out of time. Let me just say there are proposals. We made a proposal many years ago. Well, not many, 5 years ago, to measure this in experiments. You need to evolve with the Hamiltonian and minus the Hamiltonian, which is like forward and backward in time. So maybe not surprising. There are a lot of other proposals. I was involved with some of them. And there are by now quite a few experiments. The earliest appeared in 2017, trapped ions and a small NMR simulator. The biggest that's been done so far is the Google processor. Just this year released data with 53 qubits, a 53 qubit processor. And what I was going to talk about was experiments in NMR. I had lots of fun graphics. Let's not worry about that. In nuclear magnetic resonance, it's possible because of the structure of the dipole-dipole coupling to effectively reverse time. This is an old story called the magic echo. It goes back to the 70s. It's a generalization of spin echo to many body context. And what we were able to show recently is, this is a paper that hasn't appeared yet, but will appear soon, is that what they can measure in NMR are OTOCs, or commutators of global operators. So the total spin at time 0 with the total spin at time t. So for the whole rest of the talk, for the whole prior part of the talk, I was talking about commutators of local operators, operator at x with operator at y, some localized thing. Here, what they can measure as total commutators. But we're able to, with some theory, reduce that to sums of local commutators and predict a precise power law for how this thing glows. And that actually matches the data that has been taken recently. There's actually a lot of data here, but I'm just showing you one recent example. And because the dipole-dipole interaction is power law, not strictly local, there's actually a prediction from a theory we did of this scrambling physics in power law systems. There's a prediction that the growth is faster than ballistic. So we actually have a sharp prediction that you could test in a quantum simulator or in MR experiments if you could go to longer time, or maybe with cold polar molecules. We have a sharp prediction for how the picture I presented in this talk is modified by the dipole-dipole coupling. And that prediction is that the information grows not ballistically, not even super ballistically, but actually almost exponentially fast. So it's a really novel thing that has not been seen in any context, but we can access with this theory.
So any power above some, if the power law of the interaction is above some power, you get exponential.
That's right. Yeah, if the power is high enough, so that's shown this phase diagram here. In dimension d, if the power law is bigger than the dimension plus a half, then it's a like linear light cone again. If it's between these two, you get a power law, like super ballistic, but power law light cone. And then if it's even lower, you get some kind of exponential form. So actually dipole-dipole interactions in 3D are right here, the special marginal case. It's kind of interesting. And you predict a funny stretched exponential pattern of growth. which should be visible when you go to longer times if you can do that. So yeah, thanks for letting me go over just a minute or two. To summarize, I talked about chaos and scrambling. I tried to give you a recent snapshot of the theory of this butterfly effect, and to emphasize that there's been a lot of developments here, really driven by experiments, by thinking about what's possible in experiments, and also by connections to gravity and quantum information. I also try to convince you that we have a broad theory outline for this physics. And I let you know that experiments are starting to test this, and I think there's still a lot of questions we'd like to answer. And yeah, some of the things that are on my mind at the moment include, fully understanding this story of long-range interactions, which is experimentally relevant, especially in NMR. And, going back to my motivations in the solid state, can we think about what this understanding of chaos and scrambling has to tell us about transport, for example, in strongly interacting systems? That's still a very open subject, but we have some ideas there. So thanks a lot for your attention. Sorry for going slightly over.
All right, thanks a lot. That was wonderful. So let's see if there were any questions during the talk, but any further questions? I can start off with I don't know,
I could pose one. You mentioned in the talk, which I kind of like, that if the mutual information is larger than one or whatever, larger than the information in the source, then this is a measure of entanglement. But what does it mean in terms of information? Do you have some insight to this?
What does the mutual information mean in terms of?
Yeah, the fact that in the quantum case, you can get mutual information, which is impossible classically. Now, as you mentioned, in fact,
yes,
in the case of entangled states, you get information which is larger than what is possible classically. But did you have some insight or some interpretation of this result?
What I mean,
oh, it's just a fact, and I should be happy
clear
with
to you,
this.
but just so everyone knows, this is not something that I came up with or anything. This is a known thing. But yeah, I mean, the standard interpretation that I like is that it's really using the fact that you can have a quantum pure state, which is a known definite thing, but where the pieces are totally unknown, right? This is somehow not possible classically in some precise sense to have a state where the global state is known, but the subsystem states are not known. And that's what's entanglement is buying you.
Correct, I know this example and I appreciate this, but then it appears that the term mutual information in this context is is a misnomer or something. It doesn't really convey something about mutual information. It just conveys something else. I don't know. Perhaps you should forget about it.
No, I mean, I'm sympathetic to this line of thinking. If you really ask me to justify the phrase mutual information, I mean, I'm just computing some quantity, which people name something. Yeah, I want to think about it in more detail before trying to make a strong case.
Thank you.
So, Brian, you I see at the bottom of your slide you mentioned develop some effective field theory for chaos. What exactly do you mean by that?
Well, I mean, the idea is sort of simple. The motivation is simple enough. I claim that this ballistic growth plus diffusive broadening is generic. So if it's really something which is universal across all chaotic systems, there ought to be a pretty simple universal way of seeing that. There should be a simple theory that predicts that. Something like hydrodynamics for.
Can we think about the equation you wrote an equation for this C?
I wrote an equation which comes from a particular model. So what we'd love to do, like this equation here. Where did it go? This equation. using some like MSR or Schwinger-Keldysh like formalism, we can write down an action for this equation, right? And what we'd love to do is say, okay, let's like on general grounds, write down like all the possible terms in some effective action, and conclude that these are the dominant terms at low energy and long wavelength. Like this is an RG fixed point in some kind of generalized, effective theory of chaos, right? Then we would say, okay, we have an effective field theory reason why, this is the generic form, because those are the terms that are relevant at long wavelengths. And okay, if you zero some of them out, then you can get different behavior, whatever. But that's kind of the reason why this is generic. So that's what I was getting at there. And we have actually, I mean, this paper is in the works. We have such a formulation where you formulate, you need 4 contours instead of 2, like in usual Schwinger-Keldysh, because you need this like forward and backward evolution. And you can formulate like an effective theory of the operator size. That's going back to this comment I made about the weight controlling a commutator. Size, you mean? The weight, yeah. The number of operators that are not zero in the string. So we've formulated such a thing.
So you constrain the fact that you only maintain the information about the size of the operator and not actually the.
That's right. Yeah, we say this is the long time dynamics we care about, so we integrate out the other stuff, and we say, okay, we have some effective theory that plays by some very general Schwinger-Keldysh style rules, which all these different allowed terms, and then these terms are the terms that survive in the infrared that are the most important, and they predict the broadening. That's the style of argument. And then we can compare this to, this Brownian cluster model again, to like SYK clusters, various sets of interesting models, and compute the parameters of this theory in some, approximation.
So this, yeah, I see.
So yeah, it's like you do hydro and you write down all the possible terms in your hydro expansion, and that predicts diffusion.
Right.
So it's a similar kind of argument.
Okay, interesting. Other questions?
I wanted to ask about the spin chains that you've shown results which were mostly on 1D for the Ising spin, for example.
Yes.
Is it clear, or there is nothing very significant that happens in 2D and above? Or is it just?
It's far from clear that nothing interesting happens. This is just what we can do. Like in principle, this idea of entanglement being small outside the light cone will still work in 2D, but there you're working, with like a more complex tensor network, like a PEPS or something like that. I don't know what your background is, but some more complicated tensor network. So it's much harder to contract those. It's just even ground state problems are challenging in 2D, let alone these complicated dynamics questions. So it's a hard problem to do the calculation. I don't see an obstruction to it. If you have a real penchant for tensor network numerics, I think it might be possible, but no one's tried it yet. In terms
2D,
yeah.
You can do 1D.5, right? Like along something with a few.
Yeah. So there could be some interesting intermediate time physics. We would expect that the very longest times are going to really be dominated by the one-dimensional character. But there are sharp predictions. So like the picture in higher dimensions that you have a stochastic surface growth problem instead of this random walk of the front, which is KPZ-like. That's the idea in the appropriate dimensionality. And this has not really been tested for any model, apart from random circuits where it's just derived. It's just a derived fact in those models. So there's no Hamiltonian for which people have explicitly confirmed this claim in higher dimensions. And in particular, it's possible also that there could be competing fixed points. There could be the KPZ fixed point is 1, but there's also a non-broadened fixed point, maybe in high enough dimension. So it
spatial dimension.
Sorry?
Spatial dimension or local dimension?
In high
Spatial
enough dimension. In high enough dimension.
of the lattice.
Yeah, there could be like an upper critical dimension for which you don't have
yeah.
the broadening anymore. So none of this is known.
Okay.
There are predictions from the random circuit models, but no explicit confirmation in any model. So I mean, if you could do the calculation, it would be interesting. But we just
What's the prediction from the random circuit model? Is that for any dimension you will have this broadening, or is it?
What the random circuit model predicts is that it gives you a surface growth problem in general dimension, which seems to be in the KPZ universality class.
In any dimension.
In any dimension. But what's not clear, so in 1D, we sort of have a pretty strong sense there's no other fixed points, like everything flows to that. And here the KPZ is sort of trivial, it's just Brownian motion. And probably that's true in 2D as well, and maybe 3D, I don't know. But it's also possible there can be other fixed points so that you don't, this surface growth problem is only like maybe only one possible effective theory, and there could be others. We don't know. So, you know, in 10 dimensions, it's possible there are Hamiltonians for which the front is not broadened at long distance or broadened in some different way than what you'd get for the surface growth problem, because the fluctuations are sufficiently weak.
You mentioned
Is there? Oh, go ahead. Sorry.
Oh, go ahead.
So there was the fact that the dipoles in 3D, there was the interplay of the interaction and the dimension.
Yes.
So could there be like a mean field limit at some point?
Yeah, I mean, if you where's the phase diagram I put? So if the power law is sufficiently slowly decaying, so like this region down here is more mean field like, and then as you know, for a fixed dimension, as you increase the power law.
Yeah.
So if you had like a chain of dipoles, that would be more like local, I would say. But if you could somehow decrease the power law in 3D or something like that, then you could get into this more mean field limit.
You mentioned, Brian, that there's some sort of Floquet synthetic dimension realization for this physics. Do you remember what that was? That was on one. If you don't remember, it's fine. I'll just look it up.
This was
on one of your slides.
Yeah. This is an experiment in Bryce Gadway's group, I think. Yeah, if I remember correctly. So they were doing some BECs where they use momentum states to form like a sort of a lattice, and then they interpreted those as like spin states. So this was essentially what this was looking at as a kicked top, a quantum Hamiltonian for a kicked top with like 7 states maybe, or something like that. I forget the details. Maybe a bit more.
I can look it up. Yeah.
Yeah.
All right. Other questions? Okay, Brian, I think it was a really interesting talk. Thanks a lot.
Thanks for having me. Yeah.
Yeah, and hope to meet you soon.
Yeah, hopefully.
All right, have fun in Brandeis. Yeah.
Thanks. See ya.
All right, see you. Bye.
Thank you.
Thank you very much.
Yeah.
Bye.